Welcome back, Calculus 2 students. In this video, we're going to discuss the second derivative and concavity with parametric curves. Let's begin with equations x equals t squared plus 1 and y equals e to the 3t minus 5. Now, ultimately, we want to find the values of t for which the curve is concave up. Before we get there, let's go ahead and find our first derivative like we did in the previous lesson, because we're going to need that information anyway. So x prime of t is equal to 2t, y prime of t is equal to 3 e to the 3t. And we learned in the last video that if we wanted dy dx, that we needed to compute 3y, y prime of t over x prime of t. So 3 e to the 3t over 2t. So if we want to discuss concavity, we have to think about second derivatives. Let's talk about how we don't do this. First of all, some common student errors are to assume that if this is the first derivative, that we just have to take the derivative of that. So let's write no to the idea of just differentiating this fellow, or if you prefer the prime notation, that's not going to do the trick. Another misconception is that we're going to use y double prime over x double prime. That also is not going to work. So before we get started, let's make sure we understand that the second derivative we seek is not found by just taking the derivative of this guy or by using two second derivatives in a quotient. Let's think about what the second derivative of y with respect to x actually means. So if we want to understand where the curve is concave up, we need to understand the second derivative of y with respect to x. And once again, this is something that maybe you previously called y double prime, and you don't like this notation so much. But y double prime is ambiguous because it could be y double prime of x or y double prime of t, and we want to avoid those ambiguities. And so as much as you might not like it, this is the notation I'm going to use, the Leibniz notation. But what does it actually mean conceptually? We've learned that if we took the derivative with respect to x once and got the first derivative, we just needed to differentiate again to get the second derivative. And so if we differentiate with respect to x, the first derivative, we've got our second derivative that we need for concavity. Now we learned how to differentiate something with respect to x and got a formula with t values previously. When we had to differentiate y with respect to x, we used y prime of t over x prime of t. So the derivative of y with respect to x, and this is just another way to write dy dx, that turned out to be y prime of t over x prime of t. In other words, if we differentiate this fellow with respect to t and divide by the derivative of this fellow with respect to t, we're in business. So what we need here is a derivative of this guy with respect to t on top, and the derivative of x with respect to t on the bottom. And so this is still our x prime of t. We're still going to divide by x prime of t. Where we're going to vary our approach is that the numerator is not going to be a second derivative of y or some other formula with t. It's going to be this precisely the derivative of this guy with respect to t. So let's carry that out. We're going to have a big fraction, and the easy part is the bottom. That's going to be the x prime of t that we found before. Now the top may be a little bit messier because it is supposed to be the derivative of 3e to the 3t over 2t. So let's pause here. In these parentheses I have the dy dx in terms of t that I found before, and I'm going to differentiate that. On the bottom, I've got x prime of t, just like I did before. So we're going to use quotient rule to compute the derivative here we need for the numerator. On the bottom, we have 2t quantity squared. On top, we have the derivative of 3e to the 3t times 2t. So we're going to have 9e to the 3t times 2t, and then minus, and now we're going to differentiate the 2t and multiply by the numerator, 3e to the 3t. Obviously, we want to clean this up a little bit. On the very top, I'll just try to factor out as much as I can. So, of course, I see an e to the 3t everywhere. I also see a 2 and a common 3. So let's factor out 6 e to the 3t. And that's going to leave us a 3 minus, I guess it's a 3t minus 1. Now, if we're going to multiply by 1 over 2t, that's going to give us 3 copies of 2t on the bottom multiplied together. And of course, we could do one more step of simplification if we like, dividing both by 2. So this is going to be one form of the answer for the second derivative of y with respect to x. So before we do anything else, let's remember, if we want the derivative of y with respect to x, we have to differentiate our prior derivative with respect to t, and then divide by dx dt. Now we're ready to actually answer the given question. Find the values of t for which the curve is concave up. What we need is this fella right here to be greater than 0. So let's make a note of that. So we need d squared y dx squared, which is equal to 3e to the 3t times 3t minus 1 over 4t cubed. We need that to be greater than 0. Now 3e to the 3t is greater than 0 on the entire real line, so that's not going to affect our sign. More important are going to be these fellas right here. 3t minus 1 is going to be greater than 0 on, now let's think about this for a moment, 3t minus 1. Whenever t is rather large, this will be positive. Where is this equal to 0? At 1/3. So you could solve this inequality directly, and you should be able to get 1/3 to infinity. It's going to be less than 0. Maybe I'll put that over here. No, let's do it right here. For minus infinity to minus 1/3. On the other hand, 4t cubed is going to be greater than 0 for all positive numbers, and it'll be less than 0 for negative numbers. In order for our second derivative to be positive, we're going to need both of these to be positive or both to be negative. So let's see what kind of answers we get out of there. We have 1/3 to infinity and 0 to infinity. Where do these overlap? 1/3 to infinity. Down here, we have minus infinity to negative 1/3 and minus infinity to 0. The overlap between those conditions will be minus infinity to negative 1/3. So on minus infinity to negative 1/3, and on 1/3 to positive infinity, the curve is concave up. Now there's a little bit of algebra in here, and so you might want to re-watch the video or work it out on your own scratch paper. If you have any questions, be sure to contact me or post in the forum on My Open Math to see if anyone else can answer your questions. Obviously, I could have made a mistake as well, so chime in if you think I've made an error and I need to make a correction in the comments. But this gives you an introduction to computing the second derivative and also how to compute things related to concavity when you have parametric equations.